So by now you must have already started with the simulation, and you must be having some doubts in your mind as far as what are the simulation issues that you may face. Of course, if you have started with the simulation, have you started with the simulation part at this moment, up to this point, guys?
Yes, sir.
You must have started it, right? And maybe what exactly is this simulation? That is what we are going to see for the rest of the lecture. Okay. Are you able to see the screen simulation issues?
Yes, sir. It's visible.
Okay. Okay. So there are various simulation issues, and we'll start with one by one. Simulation, the concept of simulation itself, the process of simulation, the delays that are modeled in simulation, and the types of simulation. So simulation is a functional emulation of circuit design through software programs. You must have already used simulation at some point in your study so far. For example, multisim or maybe Proteus, you must have used the simulation tools. Okay, what are those tools? Basically, what they do is they functionally emulate your circuit design. Okay, and how they do it? They use models to replicate how the device will perform in terms of timing and the results. Okay, so we do have some certain models associated with the corresponding component, and that model is the thing that is simulated. So basically, you must have a model with you. Okay, then only you will be able to simulate it. So this is the textbook definition of simulation. What does simulation do? It eliminates the time consuming need for constant physical prototyping. Now, simulation is a wonderful tool. In fact, in my undergrad classes, I normally give a lot of emphasis on usage of simulation tools, specifically multisim and then Proteus. Okay, those are for the circuit designs. And simulation, why the simulation is important? Because as you can very well understand that um, we cannot we cannot prototype everything as hardware and then test it, and if there are any problems, then again go and correct something. Okay, so the simulation is a very important step just to verify whether your functionality has been met with or not. In fact, not only functionality, when it comes to digital design, timing is also a very important aspect, specifically in the clock systems, and then you can very well simulate those things also. So simulation can be performed during all stages of verification. Most of the times what we do is we have different modules. Okay. Now design in larger companies and your different bigger projects, the entire design is not carried out by a single engineer. Okay. So it's quite possible that your team leader, team manager, whatever you would like to call him, he may disseminate some smaller tasks, okay, to his subordinates, and then the small modules, then he will later on um, collate and then build the bigger system. Okay, so you will be having different, let us say, blocks with you, and that those blocks have to be simulated separately. That is what you can do, and then all stages of the design you can have this kind of simulation. What do you mean by all stages of verification? It means right from start, how to take which component to select, and all those kinds of things. You can start with that, and then whether you are happy with the simulation, the performance, you can go back and change the components. Okay. Motivation of simulation comes from need to verify that your code, that is your design, hardware description design, is correctly implementing the design. So we are checking the functional part of the hardware. Just one sec, please. All right. So this is basically the driving force for why to use the simulation. It will simply verify the design and see whether it meets the required specification. Now remember that we always start with specifications. The design always starts with a specification. Okay. For example, if you start with the design of a simple let us say linear power supply. Okay, what are the various specifications that you start the design with? Can you answer this? You must have studied design in your lower classes.
Output
So can you
level.
please? I'm talking about a power supply, linear power supply. I don't know whether you have been taught this in a proper way, because design is never taught in a proper way in most of the colleges, unfortunately. Okay. So, anyways, um, you just try to answer the question. So that let me find out whether what kind of uh, concepts you have gathered so far.
Like
Yes.
specifications like output range, like
Output range of what?
of, of voltage,
Exactly. So you be specific. Output voltage.
output voltage
Then
range.
range. Don't say range because you're talking about a power supply with a fixed output. Okay. So it's
Okay.
output. Output voltage. Then we are supposed to power, let us say, a TTL circuit. So TTL is always 5 volts. So what is the other specification? Tell me. Is that the only specification that you have? Guys, please answer. No. This is only the part, very small part of the entire specification. Please remember that the specification, whenever you start with design, you should start with the specification. Now, specification in case of linear power supply will mean the input specifications. There are three classes, I say roughly three classes of specifications. Input specifications, then you have the output specifications, and you have the ambient specifications. Okay, in input specifications, what is to be understood or written or interpreted is that since we are living in India, we want to operate this power supply in India. So the input voltage is always going to be 230 volt RMS. Okay, single phase and 50 hertz. So this 230 volts RMS single phase 50 hertz is a part of input specifications. Understood, guys?
Yes, sir.
What about the output? As somebody had said, 5 volts, but okay, that's all right. Output voltage is one part. Second part is the maximum load current. It is also called as the rated current. Maximum load current. So this load current requirement comes from the user end. For example, there is a customer who wants to power up, let us say, and he wants to drive some kind of a circuit which demands a maximum of 1 ampere. Okay, so he will say, okay, my maximum load current is going to be 1 ampere. So this is one specifications, 5 volts, 1 ampere. And there is one more important specification that normally people don't understand properly, but in industry, this is of utmost importance. And that is, yes, anyone? Output voltage हो गया, output load current हो गया. What else?
Okay, efficiency.
Sorry?
Efficiency.
Efficiency? नहीं. When you rectify the output voltage, do you really get exact DC?
No, it's ripple fact, ripple.
Yes, that ripple content is very dangerous. And this is the another specification as a part of output specification. It is so the user will say, the customer will say, okay, the maximum ripple content allowable at my end is this much. For example, 5 millivolts peak to peak, or 10 millivolts peak to peak, or 100 millivolts peak to peak, depending on his requirement. So he will say, your power supply should give me 5 volts if I should draw 1 ampere current out of it, and the ripple content in the output should be less than, let us say, 50 millivolts peak to peak. So this completes the output specifications. Understood, guys?
Yes, sir.
What about the ambient specifications? As the name suggests, it will tell
Temperature.
you, it will tell you the operating conditions, environmental conditions of the power supply. That is whether it is to be used in, let us say, the ambient temperature is 40 degrees, and then probably the humidity that it is going to have, environmental conditions like humidity is there. Then is there a requirement of an IP level enclosure that is conforming to some IP standard, for example, IP65. What is this IP65? It is a standard for the enclosure for your entire system. Anyways, so that decides your enclosure. So basically, you always start your design with specifications from the customer, input specifications, output specifications, and the ambient specifications. So in our context, that is digital design, the specification has to be interpreted properly. So here, most of the times, current voltage, all those specifications will not be immediately relevant, but the specifications provided, or let us say written by you. In fact, the concept is to write the specification is a one important task. The customer will tell you in plain English language, this is what I want, and you have to interpret that. And as a design engineer, you have to write the specifications. So writing the specifications is a very important task, because sometimes if you misinterpret whatever is the customer is saying, your specifications will be wrong and your entire design may go wrong. All right. So specification is a very important thing, and these specifications, whether your circuit meets the specifications or not, will be very easy for you to verify if you use simulation. What are the different flavors of simulation? As I've already said, functional simulation, it is a functional verification of the design, but it does not give you any timing related simulation or results. Okay, so it's only functionally verifying things. Okay, specifically in combinational circuits also, it's an AND gate. That's all right, but it will verify whether it is working as an AND gate. It will not tell you anything about what is the delay. For example, what is the delay in having in changing the output? TPLH and TPHL won't be specified at this point. So if you don't include those things, it is called as functional simulation. Then you have something called as pre-layout simulation. Okay, and is a functional verification of the design, including logic cell delays. So this is basically another level of simulation where you would include the delays also. Okay, so this is more and more perfect, more let us say uh, reaching or approximating, or let us say the real hardware. Then post layout simulation, it is performed after physical place and route. So interconnect delays are taken into account there. Okay, so we have three different levels of simulation: functional simulation, pre-layout simulation. Uh, you can call this as post-synthesis simulation also. Okay, and there is something called as post-layout simulation. So there are three different types. So instead of calling it as pre-layout, you call it as post-synthesis in this case. Okay, so we can have simulation being carried out at different levels. Okay, so if you look at the entire picture, that is the entire system, then you can have a system level simulation. Okay, the inputs and the outputs will be different in this case. Then go down to a chip level simulation, which is again, it is having different inputs, different outputs, which is a part of this system. And then the subsystems, which may be a part of the chip itself, and then the module itself. So you can see there is a hierarchy here. Modules, so many different modules will make a subsystems. Subsystems, all the subsystems together will make a chip, and then you can have the system itself over there. So simulation can be carried out at all the stages. And then how are they effective, or how difficult they are? That is what this particular slide tells you. Okay, so at the module level, subsystem level, chip level, and system level, how to interpret this diagram? First of all, stimuli development. So first of all, you'll have to have some test inputs. Okay, those are called as a stimuli. Okay, it's a plural of stimulus. So stimuli development is easier at the system level. Okay, a very simple example I would like to quote is the PC itself. Okay, so if you are building a PC, the complete entire simulation, rather let us say the working of the PC will be a very simple task, because whether it boots or not, whether it accepts the inputs from the keyboard, whether it displays properly, so the simulation is easier at this level. Okay, or rather the stimuli development itself is easy. Whereas if you go towards the module level, each level, each part of the system, then the stimuli development becomes progressively difficult. Okay. However, simulation efficiency, if you see at the system level, the efficiency is less, whereas the simulation efficiency is very high at the lowest level. Nature of detected problems, all kinds of problems are detected at the systemic level, whereas at the module level, which is the lowest level, you have the low level kind of problems which are detected. Bug correction time is very high in system level because you don't know what exactly is going wrong, where it is going wrong, whereas at the module level, as you can see, the correction level time to correct that particular bug is going to be low, because you know this particular very small module, and you can just find out what went wrong with that time in the project. So when do you do this simulation? Module level simulation is done very early in the development stage, whereas system level, obviously, when all the modules, subsystem, chip, everything is ready, then only you'll be going for the system level simulation. So these are basically the pointers as to the what are the different types of levels at which the simulations can be carried out. Now, what are the steps in simulation? First of all, you go with the elaboration, then you have the initialization and the execution. Now, this may be directly seen whenever you simulate something, in at least in active HDL, these stages are given as log entries. Okay, elaboration is finished, initialization is finished, and then the execution is finished. All these are available for the user to see in the logs. Okay, Xilinx, I don't use Xilinx, so I don't know whether these are explicitly given or not. But these levels are sometimes hidden from the user because it is transparent, or it is made transparent. Okay. So what are these steps? The first thing that your compiler will do is it will compile, check the VHDL source code to check syntax and the semantic rules of VHDL. We already have seen what is syntax and what is semantic. Syntax is the proper way in which, let us say, the grammar of the language, whereas semantic is the meaning, whether it is meaning properly or not. Okay, so sort of, if you compare it with the conventional programming language, syntax checking one side and the logic or the algorithm checking on the other side. So in VHDL, since if it is semantic rules or semantic, let us say, semantic errors, are most of the times you have to design a test bench for that and see what happens. Anyways, if a syntax or semantic error occurs, then the compiler will flag off an error message for you to go back and correct that particular part of the code. Else the compiler generates an intermediate code. So this is the very first level. So semantics is the science of meaning and syntax is the mechanism of the language. Please understand this. Okay, then the next step is elaboration. Ports are created for each instance of a component. So whenever you are having components being described in the code, in the design, ports will be created. Then naturally memory storage is allocated for the required signal. Interconnections are specified and a mechanism is established for executing the VHDL process in proper sequence. This is what the elaboration does. Then you have the initialization. Initial values preset in the declaration statements. Sometimes we declare these, let us say the generics and all that we declare right in the beginning. So all these values are initialized and are assigned to the signals of the variables. Then next part is the execution. Every process is executed until it suspends. Okay. Signal values are updated only after this. The simulator will accept simulation commands like run, assign, watch. So you can have, let us say, a command line interface is also there, which most of the times is not used that much, but then you can always have. It is something like P spice. People I must have used. You must have used the P spice or spice somewhere. Yes.
Yes, sir. Yes, sir.
So spice actually initially is some kind of a language where you have to input all the commands manually. Okay, and later on people started making use of the graphical user interface for this spice, and then came out with this all the GUI based simulation programs. Otherwise, in in older versions, you had to manually type in the commands. Anyways, so you do have that facility also. Simulation ends when all signals have been updated and new values have been assigned to the signals. So this is basically what execution does. Right? Then we must have basic definitions of some important keywords. That is the event. So what is an event? A change on component output that will be propagated. This is called as an event in the jargon for simulation as far as any HDL simulator is concerned. Then you have something called as transaction, a change of component input that does not propagate. So event and transaction. And there is something called as scheduling. So future events generated by evaluation of a process. So this is another important part of the process of simulation. So it will anticipate or it will generate the future events by evaluation of the process. Okay. Evaluation is the another important thing. Calculating the outputs of components based on inputs and the current state. So this is the core which does the actual calculation of the output. Another important thing which I would like to introduce at this point is whenever we start with simulation, uh, simulation you have two different things that you have to have in the back at the back of your mind. One is the real time and the other is simulation time. Real time is as it happens, as I'm talking to you in real time. Okay, and then you have something called as simulation time. Simulation time is always relative to some arbitrary t equal to 0. So in the simulation world, in the world of let us say computer, whenever your simulation starts, okay, that will be called as t equal to 0. All right, and its time may not be the same as the real time. Please remember this because it takes some finite time for calculation. All these steps, as we have already seen, scheduling, evaluation, okay, all this takes some time, real time for calculation. Your simulation time and real time will never match. Okay, so in simple plain words, let us say 1 minute that happened in the real time, in simulation time it may take 5 minutes of real time, but still it will be indicating that okay, this is the output after 1 minute. Okay, because its time frame is different. Are you getting this? Don't get confused, guys.
Yes, yes, sir.
So have you understood the concept of real time and simulation time?
Yes, sir.
Why there is only one person actively responding? What happened to the others? All right. Okay. So simulation will execute like this. At t equal to 0, all gate outputs are set to an unknown value. Then there are two queues which are set up. In one queue, you will be have signals to be updated and other queue processes to be executed. So two queues are there. This is what the queuing and the scheduling takes place. So when simulation time is incremented, what happens? Now we have to increment the simulation time. It is automatically done from reference as t equal to 0 whenever you start with the simulation. What happens? Signal is updated. All processes sensitive to that signal are placed on this queue that is called as a process execution queue. Each resumed process is executed until it suspends. Effect of the logic changes that have occurred as a result of process executions are evaluated. Simulation time is set to the next event in queue or halted if simulation time gets exhausted. So you'll see that you can simulate this for certain duration of time, and correspondingly the simulator will carry out these steps. Now this entire step, simulation time is, you start with the signal is updated and ends with the simulation is halted, or if the time is exhausted, or if simulation time is set to the next event in the queue. This entire cycle is called as a delta cycle. This is a jargon which is used in VHDL. So you have the delta cycle. So that brings us to what very important concept of what is simulation delta. Okay, people use this word very often. Several logic changes occur simultaneously in a circuit. In real circuit, what happens? It is a concurrent behavior which we want to emulate. But your basic processor on which you are simulating all these things is not concurrent at all. It works sequentially. So you have to have a mechanism so that all these concurrent events will appear as if they are appearing concurrently and are being executed concurrently. Okay, so to take care of this, time is actually frozen within the simulator. Okay, so you have a time, for example, t equal to 1 nanosecond. This 1 nanosecond actually is spanning, let us say, maybe half a second wide. Okay, so whatever is happening in that particular real time, the events that are occurring in the real times will be considered as the event which is occurring at this 1 nanosecond time instant. Are you able to see, understand this? Very, very important. This will, you will understand how the simulation, in fact, not only for VHDL, for every other simulation tool. Is this clear to all?
Yes, sir.
Okay, so what is happening is this time event of 1 nanosecond is expanded in real time as, let us say, half a second, or maybe depending on the speed of your computer. And then whatever is happening in that particular time slot is considered to have happened in that 1 nanosecond mark. All right. So the real time the simulator takes to complete all such concurrent operations in the queue is called as the simulation delta. This diagram will clarify more things. As you can see here, so 0 nanoseconds to 1 nanosecond, so many delta cycles will appear. So whatever is happening here in the real time is considered to have happened at this instant of 1 nanosecond. Okay, and so on and so forth. So the minimum time interval possible for the simulator is assumed to be 1 nanoseconds here. This is the discrete level. That is, I'm simulating the behavior at an interval of 1 nanosecond each. So between 0 seconds, 0 nanoseconds and 1 nanoseconds, whatever happens will be your simulation delta. So summarize this, simulation deltas allow ordering of events that occur at the same simulation time during simulation. These simulation deltas are infinitesimal amount of time used as synchronism mechanism. This is very important. When zero delay events are present, that is when events are occurring concurrently. Okay, so that is the importance of simulation delta. Without simulation delta, it is not possible for us to simulate the concurrent behavior. Then other important things which we see are how to model the delay. Okay, so delays are timing parameters given by the user for modeling physical characteristics of the hardware. Okay, so let me put a question in a twisted manner. Why do we want delays? Delays are unwanted, no? So why do we want to go for delays? Why do you go for delay modeling in the first place? Tell me, come on. Guys,
Hmm.
Guys, answer me please.
No idea, sir.
No idea. Come on. Others? No idea from. I mean, you don't have any idea about this. It is as simple as that. It's a model. You want to model the behavior of the real hardware. The real hardware will have a lot of delays. So you have to have a mechanism to model the delays of the real hardware so that your simulation will become more and more closer to the real stuff. Understood now?
Yes, sir.
So there are different types of delays mechanisms, or let us say the models: inertial delay and the transport delay. Delays are specified in signal assignment statements only, and delays should not be used in variable assignments. Please remember this. So what is this inertial delay? It is used to model the inherent inertia of the physical device. Example: the input value must be stable for a specified minimum pulse duration before the value is allowed to propagate to the output. So this is how you have the requirement of the inertial delay. If the input is not stable for the specified limit, no output change will occur. So basically, we need to have some mechanism to model this kind of behavior, and that is the inertial delay. What is the transport delay? It represents pure propagation delay, that is the wires and the interconnect delays. Signal value is assigned with a specified delay independent of the width of the input waveform. So this is how the screenshot, the simulation output will be there. You see here, Z1 is a signal. It is assigned X after 10 nanosecond, but there is a keyword called as transport here, indicating that it is a transport delay. What does this mean? You see here, Z1 is assigned X. X is your input. So Z1 is assigned X after 10 nanoseconds. So you can have a look at this thing. This is a 10 nanosecond duration. So Z1 will be asserted after 10 nanoseconds. Of course, it will go on in the same way. So we have a shifting of the pulse here. So output is shifted by 10 nanoseconds. That is what the transport delay does. What about the inertial delay? Z2. So there is no keyword. So the default is, if you don't write anything here, it will be treated as an inertial delay. So X after Z2 is assigned X after 10 nanoseconds. So as you can see, Z2 is assigned X after 10 nanoseconds. That's fine. But then where is this other pulse? This other part of the waveform. Where is it gone? It will not take into consideration this because it is less than 10 nanoseconds. Okay. We have already said that for inertial delay, the input signal should be stable for quite some time before you assign the value. Because this is not equal to or greater than 10 nanoseconds, these pulses are ignored. Okay. So this is a different type of delay. You can see the output, the mechanism is different. Okay. There is an interesting thing, interesting keyword called as reject. So Z3 is reject for nanoseconds, X after 10 nanoseconds. So it is a delay with specified rejection pulse width. So I can reject a pulse which is less than 4 nanoseconds, but I can retain a pulse which is more than that. So that is the reason why Z3 follows X, but it rejects this pulse 3 nanoseconds, which is less than 4 nanoseconds, but it will pass the 6 nanoseconds exactly as required. Are you able to see the differences? The output Z1,
Yes, sir.
Z2, Z3. So this may be useful to you at the time of, let us say, at the time of simulation, functional simulation. That is, all right. Okay. So again, a different type of, let us say, different view of looking at simulation. We have functional simulation, behavioral simulation, static timing simulation, gate level simulation, switch level simulation, and transistor level or circuit level simulation. Now, this is from the point of view of abstraction. Functional simulation ignores the timing aspects, it verifies only the functionality of the design. Whereas behavioral simulation, a given functionality is modeled using HDL, timing aspects are considered here. Now, this is from the point of view of HDLs. Earlier discussion was from the point of view of a generic electronic circuit. Static timing simulation, it is a built-in tool that computes delay for each timing path. It does not require input stimuli. Then you have what is called as a gate level simulation, is used to check the timing performance of design. Delay parameters of logic cells are used. So you already have all this information in the form of models, and then you can do this. Switch level. Again, this is, as I said, if you remember the abstraction levels, then you'll be able to understand at different levels you can have different simulations. So is one level below the gate level simulation, and it models the transistors as switches. Again, this is a kind of abstraction. Transistors behave like switches, but there is an analog behavior too. Okay, so this is hiding that. So this is a level which is higher than the basic physical level. It provides more accurate timing predictions than the gate level simulation, obviously, because we are looking at the transistor level simulation now. Then you have the transistor level simulation, which again goes down. So it requires the transistor models. You'll have mathematical equations relating current and voltages, and it will be solved numerically. So this is the lowest level of simulation. And of course, it requires large amount of computing resource. But at the same time, it gives analog results and is the most accurate. Again, finally, simulation time depends on simulation levels of logic, physical memory of your PC or your workstation, whatever it is, and obviously the speed of your workstation. Now, there were days where PCs were really, really slow, and what used to happen was people used to start simulation and keep it going for weeks together. Okay, if the system was a bigger one, the design was a bigger one, it used to take weeks together to complete the simulation. So that, fortunately, the speeds of the computers have gone very high in the recent years. So you can definitely make the most of it. So simulation now is more faster than used to be in the previous decade. All right. So this is as far as the simulation levels, simulation issues are concerned. If there are questions, you can just ask me the same on this topic. Okay. Guys, are you there?
Yes, sir.
So is it okay with simulation issues now? You'll be able to understand what exactly is going on during that process. All right. Okay. So we will shift over to another important thing which is related to simulation, and that is called as a test bench. So just let me start that slide. Show. Okay, are you able to see the slide now? The very first slide, test benches.
Yes, sir. It's visible.
All right. So what exactly is a test bench is what we are going to discuss for the remaining part of the lecture. Test bench is a very, very important concept. As I said, the HDL is capable of for us to, when it gives us the capability for us to even write the test bench for functional verification, even timing verification of your designs. So a design is always incomplete without verification. Please remember this. There are several ways to verify VHDL designs. Test benches are one of them. Test benches are also called as test cases. Okay, now this is a very common thing now. Test cases is used in software also, software industry also. This kind of concept is used in software industry also, specifically when you want to test whether your software module is working properly or not. You write down a couple of test inputs and then generate the outputs and see whether. Uh, so this mechanism of writing the stimuli basically is what is the test bench. So a test bench is an environment where a design, which we call here as unit under test UUT, is checked. Okay, and you check by applying signals, which we call as the stimuli, and monitoring its responses by signal probes and monitors. So necessarily a test bench will substitute the design's environment in such a way that the behavior of the design can be verified, that is observed and analyzed. Test bench will consist of these elements: a socket for the unit under test. Okay, then you must have a stimuli generator, then that is which is a subsystem that applies stimuli to the unit under test, either generating them internally or reading from an external source. And then tools for observing the unit under test responses and seeing, automatically checking whether the responses are correct or not. All right, so this is basically what a test bench will consist of. Now, to give you an analogy, in one of the companies which I worked earlier, uh, it was a television manufacturing company, and we used to have a lot of uh, the devices. I mean, the motherboards of audio sections, of video sections. Then there were different. Now it has been combined into a single board. But in those days, 95s probably, around 95s, used to have separate boards for audio and video sections. So my job was to check the test benches to create the test jig, as it is called in the hardware industry, for checking of the amplifier section, audio amplifier section. So what I did was I created a circuit, basically an oscillator, and I was just trying to give that output of the oscillator to the audio amplifier card and check its output, whether it is uh, the frequency response is proper or not, whether the audio output is up to the required level, that is in decibels, and so on and so forth. So the concept here has been borrowed from the hardware industry, it is called as a test jig. So the source itself, that is the oscillator which I had built, which was a common base transistorized oscillator, I guess, if I remember correctly. It used to give me a perfect sine wave, and then I used to find out the corresponding results in the output. Okay, so you must have such a kind of thing in VHDL as well, and that is where the test benches come into picture. The concept of test bench is something like this: you have the test bench, see the socket, that is a placeholder for your unit under test, the module that you want to test. Then you have the monitor and some indicators and so on and so forth. So if you place this and if you press the button, for example, now it is testing it, and you can monitor the output whether it is correct or not. Okay, so that is what basically the test bench means. Let us have a deeper look into the elements of the test bench. So a VHDL test bench is just another specification with its own entity and architecture. So you'll see that the test bench does have its own entity and architecture for. In addition, it has a special structure with some elements that are the characteristic to this type of specification. Remember one thing, that test bench entity has got no ports. Unit under test component instantiation is done. That is, the module that you want to test is actually instantiated. The relationship between the test bench and the UUT is specified through the component instantiation and the structural type specification. So test benches will always be of structural type. Then stimuli, it is a set of signals that are declared internally in the test bench architecture and assigned to these ports of the device under test or unit under test during its instantiation. The stimuli are defined in the form of waveforms or maybe in form of some processes. Okay. So this is how it looks like. You have the test bench entity, you have the test bench architecture, then begin. In begin, you have to instantiate the component and then go for the stimuli definitions. So how to design the test bench using a test bench? Design must be verifiable. The very first thing that you have to understand is the module that you are trying to design, trying to verify or test, in simple layman's term, is should be verifiable, should be testable. There should not be a complex, let us say, input or some obscure kind of input, and because it will become it will become next to impossible for you to generate such a kind of stimuli. Okay, so it should be verifiable in the first place. It is much more convenient to use a test bench for design verification. So basically, writing a test bench is a very complex task. Okay, because you should know what are the various possible levels, various possible inputs, and how your circuit should behave. So there are various things that you should know. So writing test bench itself is a huge task. So some guidelines for future stimuli development should be written as you progress with the design. So a very simple tip here for the designers is that as you start writing the design itself, okay, you just parallelly create some guidelines for how to test that particular part. Okay, and those guidelines will be useful for you during creation of test bench. It is a test bench which is simulated and not the unit under test. Remember that. The unit under test is only one of the components instantiated in a test bench. There is no limitation on the test bench size. So this is one important thing. The only limitation is the VHDL simulator, which is used, and its capability. So this is how you start design specification. The design process consists of design and verification phases. Objective of the first one is to create a new VHDL specification that meets the system requirement. Then the other part, that is the verification, you have the stimuli definition, where writing stimuli can be performed concurrently with writing specifications. It's a good tip, as I already said. Stimuli set should contain such set of inputs and states, the signal values that cover as much real life situations as possible. Now this is a little bit tricky because it may not be possible for you to cover all the possible combinations, but it should cover almost a majority of them. Okay. Then you have the test bench specifications, where when stimuli are specified, the specification of the test bench can be written. It will contain the stimuli and instantiation of the design system, that is unit under test. Okay. Then you have the test bench simulation. Simulation of the test bench is the last phase of design process. Here you will receive an answer to the question, does the system behave as expected? Remember that the answer received from simulating the test bench is reliable only to the extent determined by how accurately you have written the test bench and how much coverage you have done in creating the stimuli. The better a test bench is, the more confident you can be that your system is properly designed. So writing a test bench and then executing it is really the crux or very important step in the entire design. This is an example of the multiplexer. Okay, you see, I'm declaring a multiplexer here, mux 2 to 1. Port declaration, all of you know about this now. And then architecture follows. So this is how this particular multiplexer, which is the unit under test, is declared, and as far as entity and architecture are concerned. Then we have another entity called as test bench. Okay, this is the test bench declaration. It doesn't have a port declaration. See, it doesn't have port declaration, but it will have the architecture declaration starting with this component instantiation of the unit under test that we have declared here. So this actually happens to be in the work package. So we'll have entity, which is work.mux221. It will be referring to this particular entity. And then the port mapping will happen. Okay, this is how you declare the entity, architecture for unit under test as well as for the test bench. This is another example. Now it has JK flip-flop Again, you'll see that it is very same thing, except for instead of a multiplexer, I'm now trying to design a test bench for the JK flip-flop. Now let us have a closer look at the test bench for a 2-bit multiplexer. Library declarations as usual. Entity, this is how I have declared the port, that is entity declaration. A is in STD logic vector 1 down to 0. It is a 2-bit input. B is also a 2-bit input. Cell, you see that it is a 1-bit kind of input. Of course, it belongs to STD underscore logic type. And Y is another out, which is a 2-bit vector. All right. So this is how I have a 2-bit multiplexer design. What is a architecture? It's a behavioral type, so I'm giving this the name as behavioral. With cell select, so it depends on the cell. With cell select, Y is assigned A, so output will be directed to Y when A is 0, when cell is 0, and the output will this B input will be directed to the output when cell is equal to 1, and don't care when others. Okay, so this is the simple 2-bit multiplexer design. We are going to see how the test bench for this will look like. So this is the test bench code example. You can see library IEEE, use IEEE, and also all the library declarations. Test bench is end test bench. So again, no port declaration. Architecture. Here I'm instantiating, I'm declaring the component in the architecture itself called as component mux to 1, calling that the ports A, B, cell, Y. Okay, and then n component. So I'm declaring the component in the architecture of the test bench. All right, or I can refer to it like this also. Okay, same thing. Okay, so then UUT, that is the unit under test, is the component that is instantiated, mux2 to 1, and the mapping of the port. Now you can keep the same names so that there won't be any confusion. A of the port of the entity over here, which is instantiated, and the entity which is being referred over here, I'm giving the signal as the same names. Okay. Then this is the stimuli generation. So this part is the stimuli generation. So what do I test? Cell is don't care. Okay. And is 0 after 40 nanoseconds. So I'm actually generating some kind of waveform on cell. All right. So 0 after 40 nanoseconds, 1 after 80 nanoseconds, 1 after 120. So I'm generating some kind of a waveform here. Just see how I'm generating the waveform. And then A is assigned 0. So inputs also I'm assigning some values. 0, 1 after 60 nanoseconds, 1, 1 after 140 nanoseconds. See, all these are inputs. So we are talking only about the inputs, and we are going to check what is the output and whether it. So if you simulate this part, you will see one interesting thing that is happening. So as you have seen here, cell is don't care for 40 nanoseconds. Then afterward it becomes 0, and again 1, again 0, and remains 1 there. So I'm actually generating this waveform. This waveform, green waveform, this whatever you see here is being generated by this part of the code. Are you able to understand it, guys?
Yes, sir. Yes.
And then what I'm doing is I'm assigning some value to A, that is 0, 0, 0, 1, 1, 1 after some certain time intervals. Similarly, B also I'm assigning some values like this, and see what is the output. So is it what is expected? Cell is 0, cell is 0, okay, and when cell is 0, what our multiplexer should be doing? When cell is 0, output will be assigned A. So when cell is 0, output is assigned A, as you can see here. So 0, 0 comes here. But in the meantime, even if cell is low, the input A itself has changed to 0, 1, but the change is propagated like this, as you can see here very carefully. But now here the cell becomes 1, so naturally the output is corresponding to whatever is the input B. All right, so input B was 1, 1 here, so that is the reason why it is transferring 1, 1 value over here. All right, but it changes in the meantime, it changes to 1, 0, and so the change is propagated out here, and so on. So you can visually check the inputs, the outputs basically, and see whether your device is working properly or not. Is it okay?
Yes.
All right, but this is like let us say a manual kind of intervention is required. Like we are testing it, we are verifying it, but can we have something more automated? Okay, that is what we will see next. So using the assert and the report, we can have some kind of automation to test whether the output is as per the requirement or not. So instead of manually checking it, you can use these concept of assert and report. So again, library IEEE, the same thing. Okay, behavior architecture for Testbench. Okay, then I'm calling the component here. Same thing, exactly the same thing. Component instantiated here. Now I'm writing a process where cell is don't care, A is 0, 0, B is 1, 1, wait for 0 nanoseconds. That's fine. I'm generating the conditions. Assert y is if y is equal to, if y doesn't change, this is y is not equal to xx, you have to report that the test has failed on cell which is don't care. It simply means that if x is don't care and y is y, at that time y is not don't care, then this thing has failed. Okay, so please understand this carefully. So if this condition is not there, it will report something like this. So you can write on your own to indicate what has failed. This gives us a kind of automation to your test bench. Similarly, cell is 0, wait for nanoseconds. What you do is make cell equal to 0 and wait for 40 nanoseconds. And then after that, if y is not 0, because it is y is expected to be 0, no? Cell is 0, so y is expected to be equal to A, which is 0, 0. And if it is not, then you have to write, you have to indicate that the test has failed. Even if cell is equal to 0, y is not reporting 0. And so on. So you can understand this now. Just make sure you understand this statement properly. Assert y equal to xx report. If this condition after assert is false, then it will report or it will print something after that. This is the concept that you have to understand. And you can give a lot of indications. What has gone wrong? Okay, something has gone wrong, but what has gone wrong? So you can write here, the test failed on cell equal to 0 and there was no change in A. So A has changed, but Y has not changed. So you'll say that A has not changed in the, A is not capable of changing the output. Or you can write whatever you want. So you can make it more intuitive. So this is what has happened. You can see. Well, this is a better way of doing it. You can have these outputs in a particular way. Now, active HDL doesn't support this kind of thing. For this test benches, I use another software called as I use another software for that purpose, which is also a very famous software. Just let me fire it up. It is called as Model Sim. Model Sim is another software where you can write and verify your designs. Just wait a minute for it to come up. Just a minute. The layout is not getting okay. Try to load. Anyways, there is something wrong with the software. But what you'll see is necessarily this kind of error report. Wait a minute. All right. So this kind of error report you'll see after you use this test bench. So you can see here that I've purposely modified or made it wrong so that the outputs will be, the error will be reported. That is what is happening. Let me see if I can show that in real time. So in order to have let us have a summary. Testbench thus is an effective built-in tool for verifying VHDL designs. Troubleshooting becomes easier and faster because of assert and report, and automation of verification is possible because of the integration of the language elements. So that is the importance of Testbench. Let me see if I can show you the model sim example. Just hold on for some time. I'm unable to locate this file. That's the problem. Just hold on. No, it seems I'm not able to locate that file. Anyways, so start practicing with the test bench as well. All right. Okay. Fine then. I'll stop here for today. Two important concepts we have seen so far. That is the simulation issues, which consists of simulation delta, and the second one, that is the test bench. Test bench will become very important for you when you actually go for bigger designs. Writing test benches will be a very, very interesting and involving task. Okay. So with that, I will stop here for today. Thank you.
Thank you, sir.